Hi Year 12s, so we're looking at subtopic 3.5, carboxylic acids today. So to begin, you can identify a carboxylic acid by noticing that we have a carbonyl group, which is our C double bond O, that is directly attached to a hydroxyl group, so our OH group. Now, when it comes to naming them, the suffix is oic acid, so you put oic acid after the base name of the longest chain, similar to our other naming systems for the previous chapters. You will remove the E like normal, so for example, pentane will become pentan, because the suffix starts with a vowel. If, for example, you have two carboxyl groups, which is, we end up with a dioic acid, you leave the E back on again. So similar to the other functional groups naming. Now, I'm going to show, so this what I'm showing here is not exactly a reaction, but more taking a base hydrocarbon and looking at its carboxylic acid analog. Now, what you will see is if we take our pentane, we have our 1, 2, 3, 4, 5 carbons, and we look at the pentanoic acid version. So we have 1, 2, 3, 4, 5. One of those carbons will have a C double bond O and then an OH attached to it. And what you'll also notice is that carboxyl group, so for our carboxylic acid, they are always going to be terminal. They're always going to be on the ends because our C double bond O and then our OH cannot continue. So this stops here, which makes it terminal. So we have our pentanoic acid, which has our one carboxyl group on it. If we take our pentane, as we have here, and we chuck a carboxyl group on each end, the name will be pentane dioic acid. Now there are no numbers here, again, because our two groups must be on each end. So if we have pentane dioic acid, we know there's 5 carbons, 1, 2, 3, 4, 5, and we know that the carboxyl groups that there are 2 of, because of the dioic acid, are going to be on each end. Now, when it comes to naming carboxylic acid, our normal rules will apply. So if we look at this one here, I'm going to start counting my carbons, and I'm going to count from the carbon that is part of the carboxyl group, because that is the highest priority group. So if we go 1, 2, 3, 4, 5, and 6, that gives us our longest chain of 6 that involves the carboxyl group. So we know that this will end up as hexanoic acid. Unfortunately, I have gone over. Oh no, what have I done? Apparently I need to do that before I drew on it. So let's try it again. There you go. Hexanoic acid is our base. We then have substituents. Now we have a methyl group and an ethyl group, and we know we need to name the ethyl group first and the methyl group second. So because I'm writing my molecule name from right to left, I'm going to write the methyl group first, and that'll be 3-methyl, so 3-methyl hexanoic acid. And before that, we'll write our 2-ethyl with a dash in between, giving us 2-ethyl, 3-methyl hexanoic acid, which is this structure right here. If you do need to name a dioic acid, just know that I'll just put this over here. Oops, there we are. Just know that if we have if we have 2, obviously there's no numbering in our molecule name, but if we were to put a group on one end, we are going to give the carbon that is closest to that group number 1. So we'll start from one side or the other. That makes the substituent numbers as low as possible. If there are multiple, then we will try and get whatever numbers we're dealing with, we'll try and minimize those like we've done in our previous functional groups. Okay, now before we finish off this little section, this part is important, and that is This group, this subtopic of carboxylic acid relates to both our alcohol and ketone subtopics, because when we oxidize those molecules, they end up, or the final oxidation product is a carboxylic acid, which is what we have here. So you will have seen these before from those in those previous subtopics. So when it comes to some of their properties, I'm not going to be covering much of them, so you can find more properties in the textbooks. But they are, so carboxylic acids by their name are weak acids, are acids, but they are weak. So what that means is when you put them into, let's say, water, they will self-ionize themselves, but only to a small extent. Now, one way you can represent that is by looking at this arrow, this equilibrium arrow between the carboxylic acid reactant and our ionized product. You'll see that our forward arrow is quite small and the backwards arrow is quite large. That is showing you that the equilibrium lies to the left, which suggests that our acid is weak. If we had a base and we were doing the same thing, it would also show a weak base. Regardless, our equilibrium favors the reactant side, which makes this acid a weak acid. Now, while I'm here, I'm just going to label this one. So over here, we have our carboxylic acid is our reactant, and over here is our carboxylate ion, and obviously our proton when it's acting as an acid. So our carboxylate ion, whenever you hear carboxylate, that is our carboxylic acid with the H plus removed. Okay, so let's continue on. We are going to be looking into the reactions of carboxylic acids with three groups of other reactants. So our first one is a metal hydroxide, so that's this thing here. So our metal hydroxide, such as sodium hydroxide. What will happen is, by the way, just in case it's not clear, these groups, these reactions are generic. In other words, you can replace that R with any number of carbon, like any carbon chain, and you'll get this same reaction. So you'll end up with an RCOO minus, so our carboxylate ion, which will associate with our metal ion, so in this case our sodium. So what you've noticed is our carboxylic acid has lost a H plus, and our metal hydroxide has it has an OH, and they will combine to make water. So this is a simple acid-base reaction, making a metal salt. A metal salt and water, which we call liquid. You can represent this without the minuses and pluses and just have RCOONA as well. Either will be fine. Now, that's our first reaction. Our second one is going to be with a carbonate, so a metal carbonate, in this case calcium. There is some subtlety depending on what the identity of our metal carbonate is. In this particular case, we have our calcium being a +2 ion, and that means that it's going to need to associate with two of our carboxylic acids. So I'll just chuck a 2 at the front here, which will mean when we have our I'm going to do this version, by the way, without having the minuses and pluses, but we're going to need 2 of these to associate with 1 calcium, because our carboxylate ion has a -1 charge. Calcium ions have -2 charge. So we're going to need 2 of our carboxylate ions to pair with our calcium. So we've dealt with our calcium and our carboxylate. We are left with, so we need to account for our hydrogen here and our CO3. And what will happen is our CO3 ends up bubbling off as CO2 gas, and I'll put an aqueous for this one here and this one up here. It'll end up bubbling off as CO2 gas as well as water. calcium carbonate is a base, and our carboxylic acid is obviously acidic, so we will end up with our water and our salt, along with carbon dioxide because it's a carbonate. And that should account for all of our atoms. Yep, we have our 2 hydrogens because we have 2 of these. We have a carbon and 3 oxygens. We have 1 oxygen plus another 2 is 3. Plus we have our 2 hydrogens and our carbon. So all is accounted for. Now, we can also react them with like sodium hydrogen carbonate or metal hydrogen carbonates. When that happens, similar deal. Whenever you see a carbonate, you'll need to make CO2 come out. You'll also be making a carboxylate salt. So that is our same thing again, RCOO. In this case, it's going to be with sodium, our metal in our hydrogen carbonate. That is aqueous. We're going to liberate CO2 again. And similarly, we have to deal with our where are we? Our hydrogen, and our CO3, and we do that by all of the oxygens in our CO3 by having water as our final product. Now, if you add up all the atoms, they are all accounted for here, and so we have our reactions. Now, obviously, when you're looking at your own reactions, you'll need to consider the actual R group, so you need to make sure you have the entire molecules there. But the carboxylic acid or the carboxyl group is the thing that's doing the reaction, so all this information will be relevant for whichever actual carboxylic acid you look at. Now, the last thing we have to worry about in this little section is explaining why our sodium and potassium carboxylate salts are more soluble in water than their parent carboxylic acids. Now, excuse me, when we look at our molecules, so I'll just put in red to start with, our laser pointer. When you look at our carboxylic acid, you'll notice that it has hydrogen bonding with water. Now, depending on how big this R group is, the solubility in water will vary. So if we have a short group, maybe just 1 carbon with a few hydrogens, this molecule has is quite polar, so it'll dissolve in water very well. But if this R group was much longer, then obviously the proportion of dispersion forces to polar parts is smaller. Sorry, larger portion is dispersion forces, which will not favorably dissolve in water. Now, regardless, not really worried about that for the moment. All I'm worried about is comparing the type of bonding happening between carboxylic acids and water and our carboxylate salts and water. Now, hydrogen bonding is generally considered to be quite strong, so that is why carboxylic acids, the small ones at least, do dissolve in water well. But there are stronger intermolecular forces, and one of those is ion-dipole bonding. So we have our water molecule, which has a polarity, so obviously our delta plus and our delta minus here. Those are going to interact with the full negative charge in our carboxylate ion and our full positive charge in our sodium ion to give an overall stronger intermolecular bond between the salt and water compared to our carboxylic acid and water hydrogen bond. So because it has more favorable bonding, water doesn't mind the carboxylate salts getting in there, because when water bonds with those, it has quite a favorable interaction. And that is pretty much it for this section. Again, like I mentioned earlier, there are more details on carboxylic acids overall in the textbooks, but I'll leave those details there. Hopefully this helps.